Hi everyone, my name is Viktor Leijon. I work in the NSO engineering organization with architecture and architecture questions. Today I'm going to talk a little bit about something that I think can help you get more out of NSO. The topic is Jinja2 templates and model independence, the joys of model-driven code. So what we're going to talk about here is something that we usually just gloss over when we talk about NSO. When we talk about NSO, we have this slide as our classical slide on NSO architecture. We said NSO is model-driven, end-to-end, service lifecycle, and customer experience focused. And then we go on to talk about other stuff, about the architecture, the modular architecture, and how we can use protocols and stuff like that. But that's a small word, right? Model-driven. It's actually reflected throughout NSO and everything we do in the service management, in the device management, in the database, all our APIs, everything is model-driven. And this allows NSO to be very modular and very dynamic. But what that means is that everything we do is described by a Yang model of some kind. All the APIs are driven by the model. So when you're writing your Python code or your Java code, right, what you can do is defined by the Yang model you've loaded into your package. The CLI changes dynamically, right, depending on the schema of different nodes available in the CLI. And why can't your code be the same? Why can't you be very model-driven? And there's a natural reason why you want this, because as you start writing more and more advanced code for NSO, you want to be modular. And there are a few very common methods for being modular. You can use key-value lists. You often see lists like the one on the side here. We have a key-value list, and you just inject those as variables into a template. Or you have a leaf that points to a device template that's being applied. So you let the user customize the device template. Or in some horrible cases, right, embedding an entire JSON document in a string and just parsing that to extract the information for how to run your automation. Or other forms of tricky, right? You might auto-generate code. You might have other ways of finding information. There are catalogs and variable precedents and stuff like that. But what they all have in common is that it hides the structure of the data. It means that all those tools in NSO that we're used to, all the nice CLI, web UI stuff, all the APIs, right, they become much less useful. Because if you have a key value list and you have a template where you use the magical key IP address, then you have to have an element in your list that has the name IP address. But there's no way to know this through any of the APIs. So this information is hidden outside of the model. And what we want to do is we want to be modular, but we want to preserve all of these wonderful properties of NSO, right? But luckily, NSO has a way of doing that. NSO provides an API towards the schema. So the schema is what you get when you compile your Yang models. They make up the schema for your database and your application. So you don't actually have to know your model in advance. You can dynamically react to changes in the model. You just read the model and then do something with it. But of course, in which situations can we do this? Well, your code might be a library, or your customers might want to do customization of the Yang model, or you might want to auto-generate the Yang models and then use the schema API to have code that's not dynamically generated, code that analyzes the Yang model. Of course, in many cases, you can't do a generic job. In many cases, you want to do stuff in your code with domain knowledge, right? Where you know that certain fields mean certain things. But there are some common cases where you might want to use the schema in a more dynamic way without preconceived notions of what the model means. And we'll look at a few of those examples today. So the first thing we're going to look at is the basic schema API in NSO. It is available in pretty much all the APIs. C, Java, Python, Erlang, and JSON RPC also has a schema API. If you use netconf or restconf, then you have to use RFC 8522 Yang library instead. And that allows you to download the entire Yang model over the API and then do something good with it, right? And there are some interesting things you can do using Yang library and parsing the Yang models. So we've been talking mostly about Python today. C and Java and Python and Erlang have very similar API, where they use this CS node and CS node info structures. And the CS node and CS node info are actually reflections of NSO internal structures. So this is the kind of structured data that NSO uses for its purposes when interpreting the schema and handling the database. And there are actually very close correspondence with FXS files that you might recognize when you build your packages. You get a number of FXS files in your load there that contain this information. They are fairly primitive, right? You might want to start from these and build more user-friendly functions on top of them. And we'll go back to a more advanced way of doing this in a few minutes. But let's look at the basic API first to sort of give an understanding of what we can do here. The first thing we have here is a small example. A function isList that opens a transaction and opens that transaction as a read-only transaction. We get the node from the system and we check, is this node a list or not? And of course, the question is there a better way to do this? And there is, and we'll get back to that better way in a moment. But this is the basic thing you can do. When you have a magic node, you can take the CS node structure out of it, and you can call a method such as isList on it. And that allows you to perform interrogations towards the model and check more information about your current node. So this is the CS node structure. CS node represents a node in the schema tree. It is a very compact representation. So if you want more information, if you want to know the human readable names, you have to use the function hash to string to decode the tags and get a good string. A lot of the fields are integers are mapped into constants. So you might have to compare it to C and 16 and stuff like that. Do PyDoc NCS for a full list of the constants, and all of these nodes are available in PyDoc if you have NSO running, or as an HTML file in NSO main documentation. CS node tells you what kind the current node is. Is it a list node? Is it a leaf node? Is it a leaf list node? And it contains the tree structure of the model. So all the children of the current node is available through the CS node itself, as other CS nodes, of course. So the next interesting node is CS node info. It is more detailed information about the node. It tells you stuff like the cardinality of a list. Is there a min element? Which are the keys of the list? If it's a leaf, what data type is it? And it contains metadata for the node. And this is something that's really cool and I've almost never seen used. If you're doing model-driven development, you can use tail-less metadata in your Yang model to get extra interesting information. So, for instance, if you're building your own web UI that is model-driven, you can use the metadata tag to hide meta information about how to render the node. If you have some template process or something, you can add metadata here telling you how to handle that particular node. You can communicate using the metadata between the model writer and the developer and the code that you're writing. Okay, so let's look at a larger example, dump tree.py. So this dumps the tree of the system. So I'll show you in a moment, but it's very obvious this. You take a CS node as argument. You say, what is my type, right? What is the name? And here we use a hash to string call to translate a tag into a string. We get the type of this node, and then we print it. Just print some indentation, the type, the name of the node, and the value type, or the type value of the node. And then we recursively go through all the children and dump them at one depth greater. So what does this look like in practice? So share time screen so we can see the code. So dump tree here has these helper functions I talked about. One that checks the type of a node and just returns it into a string. One that checks the type of a leaf, and there's some magic here to say that only leaves or leaf lists are interesting. Empty leaves get a special treatment. And then we have the dump node that we saw above. And here is a small example that tries global settings commit queue. So if we go into, I prepared a little Docker container, and I'll talk more about that later. So there is this framework NSO in Docker, and I prepared all my examples in it, and I will give you towards the end the Git link for the repository. So we can run Python tree dump tree.py. It shows us everything in the commit queue container. The leaf, the name, and the type. And some case notes and stuff like that, just recursively going down the tree. We can change the path, of course, right? We can do path equals devices global settings to dump a much larger part of the tree. Spell it right. And then we get the entire tree dump. We can use this, of course, to print the tree in a format similar to the Pyang tree in a running system without having to have direct access to the Yang model. But we can also use this to do more interesting stuff. I will get to some examples of that, but this is an example of that. And you'll also notice I ran these scripts outside of NSO. They're not part of a package. And this is something that's also very useful. You can write tools using the Python APIs and just run them on the same machine in NSO to do stuff like this. You can't do services and stuff that way, but you can do tools and utilities to interrogate your system, extract information, etc. So in Python, we have a slightly better schema. We have the Magic Schema API. So as I'm sure most of you know, Magic is the high-level Python API that allows you to do much more with Python using simpler methods. So this allows you to iterate over your children, for instance. So in the node Magic object, you have a built-in iterator, you have built-in type information, and if that's not enough, you can extract the CS node member for extra information. So here is the first example on isList, extended for Magic, and instead here of using the CS node, we just check using isInstance if it is a Magic list or not. Similarly, we can dump all the children of a particular node using a a transaction, we can simply do an iteration over all the children in a particular node. We get the qualified name using the namespace prefix and a name. And for simplicity, we split it into two pieces. And we extract the name and the type of the child node. And let's take a quick look at that. So we have the other file here, isList, that contains the two isList functions and also the children method. So if we run this, we get the isList output expected and all the children of devices. The devices contains lots of stuff. The most famous part is perhaps device, but you also see auth groups and global settings. And there are a few actions and a few stuff like that. So you can get all of the schema information using the Magic API in a slightly nicer way than the CS node way. Okay, so let's move on to the final, perhaps most interesting part of this presentation, NSO and Jinja2. And how we can use this model-driven approach to get a nice, smooth integration with Jinja2 without having to pre-program anything. But let's start with a quick detour because we need one more piece to make this work. We need load native config. In a recent version of NSO, we introduced an action called load native config that's available on certain NEDs. So it allows you to input what is native config data into the device through NSO. It's not true native. What it actually does is that it goes through this parser of the NED to load the information. You're still limited to whatever the NED can handle. And you have to have NED support for this. But for iOS in particular, right, we have this, and it works pretty well. You do it in an open configuration session, so it's a config mode action. And you do something like this. Device is device, iOS 0 load native config, right? And I used verbose here to get some extra information on what was parsed and what was skipped. And then we get the corresponding configuration. This allows you to input text in a very textual format for a device, even in cases where the native config does not match the actual CLI config in NSO. So we have all the pieces. We can use the schema to extract config values. We can feed those values into Jinja2 templates using the regular Jinja2 APIs. And then we use load native config to load the rendered template. And here on GitLab is the example for yourselves. This will be available in slides and together with this presentation. So with that, let's go take a look. So we have our service code here. It's really quite easy. Extract the variables from the service using some schema logic. For all the devices in the service, get the device node and use a method I've written called template apply to apply the Jinja2 temple example.j2 to that particular device. So let's go through the pieces. For the Jinja2 templates, I have a very simple method that just renders the template into a string. And then I use a little bit of Python magic to figure out where my template file is. I just count backwards from my package to find where I am. And then I put all my templates into the Python subdirectory. So they would, when I do a package reload, or package redeploy, I would copy over my Jinja2 template together with my Python code. And then I process that. So that's it. A little bit of deep magic, but nothing terribly complicated. The other piece here is this get variables. Get variables here takes a service input. It goes through every child in the service, gets the name, gets the node for the child. We skip certain built-in names that we don't want to use as Jinja2 variables. That is modified and directly modified. They're not very relevant for us. And then we have a number of unsupported types, container, action, leaf list. We could implement support for these, but for the purpose of this demo, we are skipping them. And then we have some magic handling for lists. And if it's not a list, we simply turn the child node into a string and add it to our list of variables. If it's a list, we iterate over every instance in the list. We have some magic here to check if it's a singleton list. If there's only one child called item, then we make this into a Python list instead of a Python dictionary. If we have more elements, we turn it into a dictionary. And we go through all the children in this instance and put them into the dictionary with recursive handling of lists, as you might expect. And I have a very simple Jinja2 template. We set an IP address for gig E01. We loop over the routes and the gateways in the route and add an IP route statement for each of them. The Yang model is pretty simple. We take a list of devices, an IP address, an IP mask, and a list of routes with a list of gateways. Okay, let's look at this in practice. So I can create an instance here. Example, it's called E1, device, iOS 0. Let's set the IP address to be the master, the better, like this. And let's add a route as well. Let's say I want So I prepared a small payload. I have a tail on the log here, so we can see what's happening. Let's commit dry run out format native. So it would send pretty much what we would expect to the device. And if we look more deeply into this, we can see that we got these variables that I extracted from the Yang model. We applied a template and it looked like this after we applied it. There are lots of blank lines because of the way that Jinja2 deals with processing instructions. And we can see the result here. 6 lines were parsed, 0 were skipped. So if I just do a commit here, it will go out to devices and push this configuration. Now, what do you want to make a change from it? Well, maybe I decide that I want to add a verb. I want to add the verb secret here to my template. I said this is running in a Docker container, so I have to rebuild my test environment to get my new Jinja2 template in. It's a bit slow, but there we go. Now, if I do example E1, redeploy dry run, it will now create the verb secret as well for this route. Okay, that's nice and all, but maybe I don't want to have a fixed verb. Maybe I want the ability to destination verse. So we just add route.verse here. And then we go into my Yang model and say that for every route, I want a verse like this. I rebuild my system with a new model. And what I've done now is that I've changed the model and I changed the template, but I haven't changed any code. So this is very similar to what you can do natively in NSO with XML templates. So this is not something that's revolutionary in that sense. NSO can already do a lot of this with XML templates. This is just sort of a demo replicating some of that using Jinja2 templates instead of XML templates. And similar to Jinja2, our XML template has a lot of processing instructions and a lot of different things that you can do to make it do the things you want. Okay, so we're done the system upgrade. The packages are okay. So now, if I do example, routes R1, add a verse management here. If I do commit try run out from a native here, we now get the verse management based on the verse I connected in the model. So that is how you can work with Jinja2 templates and a model to sort of iteratively evolve your model-driven things. So to sum up, the Schema API is really cool. You get all the NSO advantages, nice CLI, input validation on all the APIs, structured payloads and all of that. The possibilities are endless. What can you drive with a model? What kind of things can you think of where you have a dynamic enough situation that the model can be used to drive your payload rather than having to precondition or pre-program a structure into your model. And there's a source code link again. So I think that's everything from me. Do we have any questions? Anything like that? Okay, go on.
That was pretty interesting, Viktor. I haven't seen that before.
Yeah, and I thought about you briefly mentioned the tail-f metadata that you could put in and could make this even more elaborate for your purposes. But metadata, when you set that, is that something that is static in the model, or is it something that you can apply when you are creating nodes?
This is static in the model. There is a different piece of metadata, the tags that's available on each data node, but this is available on the Schema node. So you can play around with adding tags of various kinds to your data nodes as well, of course, but that's slightly different.
So I was a little bit confused about, so I get what you're doing, right? You're sort of generating native config with the Jinja template, and then you do the load native to load it into the device. And I'm curious where that happens. Is that something that you just do in a normal transaction? You're not really, or it's in the create? How you?
Right. So in this case, I am actually in the create code for my code. So I skipped over this a little bit, but I mentioned that it has to be done inside of a write transaction.
Yeah.
And so what I do, right, is that I use my service transaction. I have a transaction in already. So my device node here comes from the currently running service transaction. So what this means for sort of the advanced user is that if I do example E1 get modifications we actually have the diff set as usual for my service. So this Jinja2 template will actually obey the usual fastmap rules, which is pretty nice.
Yeah, very nice. Okay, I'll have to look at the code. Very interesting.
Yeah. Thanks, everyone. Hopefully this was useful.